Welcome to the class of Introduction to Photovoltaics. In the Solar Academy course, we have PV, or Intro to PV, which includes the photovoltaic application to solar technology. We start with understanding what a diode is. It's a piece of semiconductor component which has two sides, and the electricity can flow only in one direction. So the basic of the photovoltaic cell is a diode. In a diode, we have different modes of operation. An unbiased diode works without the application of an electric voltage. A direct bias applies a voltage on the direct polarity, positive to positive, negative to negative, and the current flows normally. On a reverse bias diode, the electricity doesn't flow at all. The photovoltaic industry is based on the discovery of the photodiode. So what is a photodiode? It's a diode in which the electricity flows when light is applied to it, either sunlight or light from any other source. So when we apply the light, the diode conducts electricity. So photovoltaic is the field of physics and technology related to the direct conversion of sunlight into electricity. And so the photovoltaic itself is the operating mode of a photodiode. It's the unbiased operating mode. That means that a photodiode, like a photovoltaic cell, does not need voltage. It generates voltage when it's exposed to sunlight. So a photovoltaic cell is an array of a large area photodiode. It's a big photodiode. When we apply sunlight, we generate voltage. So what we do in a photovoltaic system is expose the sun to the solar modules. Photons, which are tiny particles of energy traveling at the speed of light, hit the solar module and actually are hitting a solar cell. And a solar cell is composed of two or more junctions and two or more layers. One positive layer has a lack of electrons, and a negative layer has an excess of electrons. That creates an electric field. When the photon hits the solar module, it detaches electrons that flow through the DC or direct current wiring towards the inverter. So if we put solar modules in series or solar cells in series, we create an array. In this case, with solar cells in series, we have a photovoltaic module for a DC to DC application. If we want to sell power to the grid, we need to connect the photovoltaic array to an inverter. And what is the inverter doing? It's interacting with the photovoltaic module. So what happens in the photovoltaic module? Some of the photons are not absorbed by the junction. Some photons have more energy than necessary to detach electrons, and some photons have exactly the correct amount of energy to detach electrons that flow through the DC wiring. So the challenge of the solar industry is to absorb more photons and so increase the efficiency in the conversion from solar light into electricity. So how was this discovered? It started with a French physicist in 1839 who discovered the photoelectric effect, not the photovoltaic effect. The photovoltaic effect is created in a junction of semiconductors. But when this started, Edmond Becquerel discovered that there was an emission of electrons when metal electrodes were exposed to sunlight. And so, experimenting with sodium and selenium, he observed that when he exposed these electrodes to sunlight, the conductivity increased. There are many landmarks in this history. We'll just mention a couple of them that are significant. From 19 1921 to 1946, we have a whole development of the theory of photovoltaics, starting with Albert Einstein, who described the phenomenon in 1904. And that awarded him the Physics Nobel Prize for his contribution to the understanding of what happened inside the cell structure. In 1946, an American engineer called Russell Shoemaker filed the first patent of the modern semiconductor solar cell. And by 1954, AT&T Bell Labs engineers developed the first silicon solar cell capable of driving electrical equipment by generating electricity when exposed to sunlight. The first application of solar cells was to the space industry. In 1958, the Vanguard 1 satellite had 0.5 half a watt solar array. This evolved greatly thanks to the application of photovoltaics to astronautics. And we can see in 2010, they had the International Space Station with a PV array of 130 kilowatts or 130,000 watts. So what is this conversion efficiency? The conversion efficiency is proportional to the power the cell is delivering in maximum power point. And is inversely proportional to the area that the solar cell takes. So the larger the area, the lower the efficiency. Some solar modules are more efficient than other modules, depending on the technology. For example, we have polycrystalline and multicrystalline silicon solar cells, which are the most common in the market. They have different appearance and they have different efficiency. The polycrystalline solar modules look like pretty much this module, where they have this appearance of a metal flake. They are composed of multiple crystals. In the monocrystalline, the silicon is pulled as a single crystal, so it looks like pretty much this solar module is completely homogeneous. And then we have thin film solar cell, which, unlike the monocrystalline, which are produced by slicing an ingot of crystal, in the thin film we have a vapor deposition, so a very thin layer of semiconductor. Those technologies have created a way to make a photovoltaic solar module utilizing very little material. So that's why it's called thin film. So to have an idea on how thin a thin film is, if a hair is about 80 microns, a thin film deposition could be anywhere from 1 micron to 10 microns. So it uses very little semiconductor material for the same conversion of electricity. Amorphous silicon is made of multiple silicon layers, and each layer is hydrogenated. It's also a technology that uses very little material to produce a high conversion. To compare the efficiency of conversion between solar light and actual DC current, we can compare the monocrystalline, which is about 24% in laboratory cells, to the polycrystalline, which is about 19%, and the amorphous, which is 14%. But the actual industry standards in production cells is between 14 and 18% for mono, 13 to 16 for poly, and amorphous 5 to 8%. So depending on the efficiency of the solar module is the number of square feet we are going to use to extract 1 kilowatt of power. So we can go anywhere from 75 square feet for mono to 200 square feet for amorphous silicon. And that is the area we will use to produce 1,000 peak AC watts. 1,000 watts is equivalent to 1 kilowatt of alternating current at the output of the inverter. So as a rule of thumb, we utilize this table, this graph, to indicate how many square feet of roof area or ground mount area we are going to use for each type of solar PV technology. So what happens with the solar module? It produces DC current, just like a battery. So we have a polarity of positive and negative at the end of the battery, and when we close the circuit, we have electricity, and that is DC current that flows in only one direction. So in order to use a photovoltaic module for a grid interactive application, for a system that is connected to the utility grid, we need to convert DC current into alternating current. So what happens with the DC voltage? In a direct current voltage, what happens is that over distances on a DC wiring, the voltage drops. So that's why we don't use DC in the public grid. What happens is that the material in the wires, like copper, presents a resistance, and so that causes a voltage drop. So that's why we don't use DC voltage to operate the public grid. Instead, we use alternating current. And what is alternating current? It's a current that flows in both directions, 60 times per second. So the alternating current reverses the flow of electricity 60 times per second, as opposed to direct current, which flows all the time in the same direction. So in alternating current, we need something to convert DC to AC, and that is a photovoltaic inverter. So what we see here is a conversion system, a conditioning system, which is a photovoltaic inverter. It operates with the solar modules with the mission of extracting the maximum power from the sun, and at the same time interacting with the utility grid to make the current compatible with the grid. So what the inverter sees when it's operating is the equivalent circuit of the photovoltaic array. So the inverter doesn't know what is a photovoltaic module, a string, or an entire array. The inverter interacts as if it were connected to an equivalent circuit, which is a diode, and the diode is because of the junction. And then we have a resistor in parallel and a resistor in series. The current flows only in one direction. The inverter interacts with this equivalent circuit, not the electrical circuit, and converts that into alternating current. So the inverter also interacts with the PV array by changing its internal conductance so that the PV array produces the maximum power point, or the maximum voltage when the maximum current is present. So the inverter interacts with a number of elements in the PV array. The smallest element is the solar cell. The solar cell has a certain open circuit voltage. If we connect solar cells in series, we have a solar module. And if we connect solar modules in series, we have a string. So a string has an open circuit voltage, which is the sum of the open circuit voltages of each module. And the flow of current is limited by the maximum current of any of the solar modules. When we put strings in parallel, we have a PV array. So when we want to add more photovoltaic power, we add strings in parallel. The current will be added as we add strings, while the voltage is the same. So when the inverter is off, the open circuit voltage of a PV array is the same open circuit voltage of each string. But when we close the circuit, we will add the current of each string. So a photovoltaic array, say of 4 solar modules, 1 kilowatt, will produce an instant power of 1,000 watts. If we put more strings in parallel, we will have more power, but the voltage is the same. So for example, here, if we have 4 strings of 1 kilowatt or 4 strings of 4,000 watt peak, the inverter will be able to produce the equivalent AC watts of 4,000 watts. So what happens with the solar photovoltaic array when it's exposed to sunlight? The inverter has to solve a complex problem. And why is that? Because of the intrinsic behavior of a photovoltaic junction. When the irradiance increases, that is, when the intensity of the solar light increases, the current through the solar module increases in a proportional manner. So that is simple. But what happens is that the power we extract from the photovoltaic array is the voltage of the PV array times the current. So the current might be easy to track, but the voltage, when the same irradiance increases, does not increase proportionally, but through this curve. So at any one point, we need maximum voltage times maximum current. So if we leave a photovoltaic array without interaction of the inverter, we will not have the maximum voltage when the current is maximum. So we'll defeat the purpose of having a photovoltaic plant. So we need an inverter to solve this problem. What happens is that the power in DC watts that we extract from the PV array equals the voltage in volts times the current in amps. But what happens when a solar module is exposed to the sunlight? The temperature might increase or decrease depending on the weather. What we observe, when the temperature decreases, the voltage increases. So the colder it gets, the higher the voltage of the solar module. And conversely, when the temperature increases, the voltage goes down, so the power goes down. So now the inverter is exposed to the problem that the voltage depends on the temperature and the current depends on irradiance. But the temperature depends on also the wind. So it's very complex to try to model in a mathematical model, in a firmware, a system that can simulate the weather. So the inverter has no other chance but to measure the voltage and the current instant by instant and interact with the solar module to create the condition in which the voltage is maximum and the current is maximum. And that is what the inverter is doing all the time, and that is called maximum power point tracking. So the inverter is very busy on the DC side tracking the maximum power point. So when we have a photovoltaic system connected to the utility grid, we have a PV array either on the roof or ground mount, an inverter that will convert the DC into alternating current. Then we have an overcurrent protection, which is a regular breaker connected to the main service entrance. And then we have a utility meter, like a bidirectional meter. When the sunlight hits the solar modules, they produce voltage, and the inverter interacts with that solar module to produce current. But the inverter only produces current if the voltage of the utility grid is present. So when we close the breaker and the AC disconnect, the AC side of the inverter checks the utility grid voltage. If that meets the definition of AC voltage by the standard code UL 1741, then the inverter will produce current. It will copy the AC voltage waveform into an alternating current and will generate that current against the wiring of that installation. So the current will meet the demands of the loads, and if the inverter produces more power than the demand of the house, the excess is injected to the utility grid and the meter spins backwards. or a net meter shows that we sell power to the grid, we have a certain consumption, and the difference between the production and the consumption. So in a grid interactive PV system, we have photovoltaic modules, an inverter, and a breaker as the overcurrent protection device. In addition, we need to have a bidirectional meter. If for some reason we had no bidirectional meter but unidirectional meter, that will cause the homeowner of this installation to receive a huge utility bill because all the production and all the consumption will be computed as consumption. So we need to involve the utility into commissioning and installing a bidirectional meter or a specific meter for feed-in tariff programs. How many watts do we produce to the utility grid as opposed to the DC watts that we produce in a solar inverter? Well, there are different standards, different measurements references to understand what is a watt on a solar module. The standard test conditions put the cell temperature at 25 degrees C, the irradiance or the amount of solar radiation at 1,000 watt per square meter, and the air mass or the equivalent of atmospheric air exposed to the solar module, 1.5. So one standard to compare two different modules or two different manufacturers is the STC, is a laboratory condition. There is another standard that is PTC or PVUSA test condition that establishes the temperature of the air or ambient temperature at 20 degrees C as opposed to the cell temperature. The irradiance again at 1,000 watt per square meter and the wind speed at 1 meter per second. And the standard operating conditions uses the same ambient temperature, 20 degrees C, the irradiance a little bit more realistic to real world conditions, 800 watt per square meter, and the average wind speed at 1 meter per second. So depending on which standard we are using, we can compare two solar modules. So when we say we are producing 2,000 watts, that means we are producing that amount of watts in that instant when we read the meter or the inverter instrumentation, as opposed to watt hours. What are watt hours? Is the amount of energy used over time. So 1 watt over 1 hour is 1 watt hour. That is a measurement of energy. 1,000 watts over 1 hour is 1 kilowatt hour. So when you buy gasoline, you pay by the gallon, but when you buy electricity, you pay by kilowatt hours. So when you sell photovoltaic energy to the utility grid, you get paid in kilowatt hours. So we see 100 watts times 1 hour is 100 watt hour. 500 watts, like the equivalent power of 5 lamps or bulbs of 100 watts each, is 500 watts times 1 hour is 500 watt hour. And if we have 1,000 watts or 10 of these bulbs and they are on for 1 hour, it will be 1,000 watt hour. So that is the unit of measurement of power that we inject to a utility grid. So the kilowatt hours and the kilowatt depend primarily on the intensity of the solar radiation. When there is more solar radiation, there is more current circulating over the solar modules. So we need to reference the amount of solar energy to the amount of power we produce to monitor and data log the performance of a PV system connected to the grid or in an off-grid system. So what is insolation? Is a measure of the solar radiation received on a certain surface, a given surface or area on a given time. So for example, if we have an intensity of 1 kilowatt over 1 square meter, which is approximately 10 square feet. And we measure that in terms of the total energy received in the day. We will express that in kilowatt hours per square meter per day. So the amount of energy of a solar day received by a PV array will be a number of kilowatt hours per square meter per day. For PV applications, is commonly expressed in kilowatt per kilowatt hour per year, or kilowatt hour per year per kilowatt peak of photovoltaic module. So depending on the location of the photovoltaic plant, we will have more or less exposure to the sun irradiance. For example, in the Southwest, we have a high level of irradiance all year round. So the irradiance at any given instant in kilowatt per square meter is very high. Consequently, the accumulated energy kilowatt hour per square meter per day and per year is higher. To maximize the harvest of photovoltaic energy, we have to orient the solar modules to the angle equivalent to the latitude of the location of the photovoltaic plant. For example, here on these graphics, we see that the sun rays hit the solar module at a certain angle respect to the Earth's surface. We are going to orient this solar module perpendicular to the sun, which is with a tilt angle equivalent to the latitude of the place, the same as this module. So all these solar modules are correctly oriented so that the angle of the solar module respect to the horizontal is equivalent to the latitude of the photovoltaic plant. As opposed to that correct orientation, we'll see here what happens with these solar modules. They are parallel to the horizontal, parallel to the ground. So in the correctly oriented solar modules, the angle between the sun and the photovoltaic module is about 90 degrees. So we will harvest more energy. In this case, the angle between the solar module and the sun is much larger than 90 degrees, so we'll receive less intensity of solar radiation, so we will harvest less photovoltaic energy over the year. So in general, the orientation of the solar module on a flat plane or on a flat roof will produce less energy, less harvest over the year than a solar module oriented to an angle equivalent to the latitude of the photovoltaic plant. To optimize the harvest of energy or photovoltaic energy converted to electricity, we have to orient the solar modules to the south in the northern hemisphere and to a tilt angle equivalent to the latitude. That will create this sweet spot of correct orientation respect to the south and correct orientation respect to the latitude. In that way, we will generate a maximum harvest. If we apply that to a location of a house, we will see that we want to capture the maximum amount of solar access in summer and the maximum in winter. For that, the solar modules have to be facing south. So we'll have an area where the harvest is maximum and an orientation, like in this northern hemisphere house, to the north will be a very poor total collection of energy. So we want to be in this area. That means that we are maximizing the solar aperture, the solar axis of the system. And for that, we have instrumentation systems that we can buy in the market to quantify the amount of kilowatts based on where we apply the solar modules. We also want to use those systems to quantify the shade. If there is exposure to the shade, then we will have more impact on the overall performance. A small shade produces a big decrease in production of kilowatt hour. So we need to quantify how much shade we have. And for that, using computerized or electromechanical systems, we can project the shades over the sun path and quantify that and tell our customer or for ourselves how many actual kilowatt hours we are going to produce. So for that, some systems take a photo from the sky and then overlay the sun path. Then once we have the sun path, we will extract the area that is actually exposed to the sun, giving us the solar aperture. On a photovoltaic module, we need to know the orientation respect to the south. We need to know the number of modules and strings that will determine the amount of power we produce, and we need to count how many spots of shade we have to actually predict the number of kilowatt we sell to the grid. So there are many orientations and mounting systems that optimize the existing architecture. Like a house with a roof, we will have a preferred mounting system flat against the roof, where there is no angle between the solar module and the roof. Or we could have a ground mount, where there is an angle between the ground and the solar module optimized to the latitude. So to summarize, to maximize the energy harvest, the orientation of the PV module should be to the south in the northern hemisphere and to the north in the southern hemisphere. The angle of the solar module should be equivalent to the latitude. And the number of modules and strings to produce a number of kilowatt hours will depend on a design computer system. So the Sunny Design is the preferred software to determine how many modules, how many strings, and the wire size to optimize the production of kilowatt hour. Then we will measure the impact of shading calculated using assessment tools, and they will come up with a number of kilowatt hours of total energy injected to the grid. Well, thank you very much.